Hi everyone, welcome to our stream. Uh, Let me make sure that everything is working fine and then we can just start. Uh-oh, I think I have some problems here. Let me just see if there's anyone in the chat. One second everyone. I just got a message that there was a problem. Try the following link. All right, hold on here. It seems to be working at my end. I'm not sure why some people had problems getting in, but I'm going to go ahead and start. If people don't get in right now, if people had problems getting in, I'll well, you can always watch it later. I do see some people in the chat right now, but I don't see anyone responding. So I'm not sure what's going on here. Oh, it says the video is private. Okay, let me edit that. All right, I think it should work now. Yeah, this one's going to have an extra long uh, header, but that I'll just put a timestamp when it starts. Okay. All right, I think it should be working now. Is there anyone in the chat? Oh, okay. It seems to be working. All right, let's start then. I'm sorry about that. I don't know why the settings switched to private. It should have been. It should have just picked up the defaults from last time. So, oh, let me just see here. You just type again. Hi, is there anyone in the chat right now? Oh, yeah, there's a few people. Okay. All right, let me start. So I'm going to start right now, and I'll put a timestamp so that people know where to start listening, so they can jump all the preliminaries. So we're only going to do 3 questions today. Okay. The I was going to do a fourth question, but we did so many of them that I thought there was really no use to it. Now they're long questions, so they're 3 long questions, I should say. But what are they? The first one is going to be a combination of rotational, of two-dimensional conservation of momentum. Okay, our second problem is going to be, where's that one? Our second problem right here is going to be a combination of center of mass, moment of inertia, rotational dynamics, and rotational kinematics. And then our last problem is going to be angular momentum, conservation of angular momentum. I'm not going to do rotational kinetic energy. We did those in class, and they're all roughly about the same. So I just didn't see a point to going over that again. Okay, so that's what we're going to do today. So let's start. All right. So let me just take another look at the chat here. Yeah, it looks good. All right. Okay, so let's read the first problem. We didn't do an example of something blowing up. We had an example of two-dimensional collision, but we didn't have something where there was something just sitting at the center and then blowing up, okay? And that we did together, all right? Now, that's what this one is, okay? So we have a 20-kilogram bomb, and it's initially at rest, okay? And I didn't say it's at the origin, but you can, assume that it's at the origin because you get to put the coordinate system wherever you want. But we'll assume that this 20-kilogram bomb is just sitting there at the origin, and it blows up into three pieces. Okay, so the first piece is a 7-kilogram chunk, and it's going to fly off along the plus x-axis. All right, so I should probably bring up my graphics program. I don't think we have to draw this one. We might. Yeah, I think we will. I take it back. We'll draw this one in just a minute. So there's a 7-kilogram chunk that flies off along the plus x-axis. Okay. There's an 8-kilogram chunk that flies off at 60 degrees to the plus x-axis at 150 meters per second. So the 7-kilogram along the x-axis at 200 meters per second, 8 kilograms at 60 degrees to the x-axis at 150 kilograms per second. So I'll draw the picture when we need to, but let's just go through the questions one at a time. Okay. So the first question is how big is the third piece, okay? And it's pretty obvious that this is just a conservation momentum problem. So, conservation of energy problem. So, oh boy, conservation of mass problem. So we had 20 kilograms to start with, and we have one piece which is 7, another piece which is 8, and so the remaining piece has to be 5 kilograms, okay? So that answers the first question, okay? Now the second question and the third question here, they go together. So we have this third piece, and we want to know what's the x component and the y component of its velocity. Okay. Now you go, geez, how do I even begin to do that? You have to recognize that this is a conservation of momentum problem. Okay. Let's draw the picture here. Okay, and let me bring up my oh, it came up. There it goes. All right, and let me make that a little bit bigger for you. Okay, so let's draw our x-axis this way. Okay, so there's plus x. And our y-axis this way. Okay, so this direction is plus y, like that. Okay, and we have this, I'll draw it in red here. We have this 20-kilogram bomb at the origin, like that. And there's going to be 3 pieces. One piece is going to fly off this way. Okay, that's your M1. All right, like that. And that's the one that is traveling along the x-axis at 200 meters per second. And then it says that there's an 8-kilogram traveling at 60 degrees to the x-axis. So remember that you measure counterclockwise. Your angle's measured counterclockwise like that. And so we're going to measure up to 60 degrees. So 60 degrees looks like that. And so here's M2. All right. And now I don't know exactly where M3 is going to be, but I think it's pretty obvious that it'll be somewhere like that. Okay. M3 like that. And it's going to have an x component. Let me draw that maybe in green here. It's going to have an x component to this velocity like this. And it's going to have a y component to the velocity like that. Okay. Remember, the components are just the projections down like that. Okay. And I'm off a little bit, but that's good enough. Okay. And so the first one is find the x component of this velocity. We'll call that v3 for the velocity of the third object, x component like that. Okay. And then the y component, that's going to be the next question. It's going to be v3y like that. All right. So let's switch back to this, and let's do the problems here. Actually, I've got it down here. Okay. So the first thing is you have to recognize that this is a conservation of momentum problem. And you say, well, what's the momentum before and after? Well, before and after the explosion. If you take a look before the bomb is sitting right there at the origin and it's not moving. So that's 20 kilograms with a velocity of 0, and momentum is mass times velocity, so that's 0, and so there's no momentum to start with, okay? And that's no momentum along the x-axis, and I should probably say that. There's no momentum along the x-axis, and there's no momentum along the y-axis either, okay? Because momentum is a vector, there's both an x and a y component to it, okay? And it's not moving in the x direction, it's not moving in the y direction, so there's just no momentum at all, x or y component, okay? Now, after the explosion, we're going to have an expression that looks like this, okay, for the x component, right there, and a similar expression for the y component, like that. And let's go through the pieces that are going into that, though the x and the y component are identical, except one is referring to the x and the other to the y. Let's go through the pieces, okay? It's m1, v1, but only the x component. m2, v2, but only the x component. m3, v3, but only the x component, like that. Now you take a look at this and you go, do I know m1, M2 and M3 to start with? And the answer is yes. You know that M1 is 7 kilograms. Okay, you know that M2 is 8 kilograms. And therefore, because mass is conserved, there's actually 3 things that we know that are conserved: mass, energy, and momentum. So because mass is conserved, the third piece has to be 5 kilograms, like that. Okay, so we do know M1, M2, and M3, but we don't know M1x, M2x, and we want to find, V1x, V2x, and we want to find V3x, okay? We don't know V1x immediately, but we kind of do, because I told you up here in the problem that it's traveling along the x-axis, directly along the x-axis at 200 meters per second, okay? So you go back to that diagram there, and you take a look at M1, the red vector there for M1, and it's directly along the x-axis, and so all of the velocity is along the x component, and there's no velocity along the y component. And so over here, when you go to break up the velocity for M1, the x component is the full velocity. It's the full 200 meters per second, okay? And the y velocity is 0. So we have V1x, that's going to be the 200, the full velocity, and V1y is 0, okay? So that was easy enough, all right? Now, what about for M2? We're going to need, for the x component, we're going to need V2x, and for the y component, we're going to need V2y. So do we have V2x and V2y? Well, not directly, okay? So if you take a look at the diagram there, you see that the M2 is at the 60 degrees to the x-axis, like that, okay? It's at 60 degrees. And so there's an x component like this, okay, to M2. I drew it a little bit too long here. Let me just do the projection down like that. So here's the x component, okay? And then there's going to be a y component like this, okay? And you see, how do I get this V2x component, and how do I get V2y component? Well, we've done this a lot of times now in the course. This is basically a vector, okay? So V2, the full vector, okay, the full velocity here, I'll draw it in, V2, which is the, whoops, that's not the right color. Let's get red here. V2 like that, okay? That's up along the 60 degree. There's an x component, V2x, which you obtain by the cosine, and V2y, which you obtain by the sine, okay? So back here, to get V2x, it's going to be the magnitude, and I tell you that it's traveling at 150 meters per second, okay, if you read the problem again. Okay, the 8 kilogram chunk flies off at 60 degrees to the x-axis, as we saw in the diagram, at 150 meters per second. So that 150 meters per second, that's the magnitude. Okay, so over here we have 150. For the x component, it's cosine 60 degrees. Okay, and if you work that out, that turns out to be 75. Okay, for the y component, it's 150, but now times the sine of 60 degrees, and that's going to be 129.9 meters per second, okay? And so I'm actually doing parts B and C together because, you know, I asked for the x component and then I asked for the y component. It's just as well, we might as well do both of them together, okay? And then what about V3x and V3y? Well, we don't know those. In fact, that's what we're asking for, V3x and V3y, okay? So let's do that. So I didn't put the primes everywhere because it kind of gets annoying, but really what I've got highlighted there is the momentum, x component of the momentum after the explosion. Okay, so I did put the prime here for that, but I didn't put it on the velocities just because it gets annoying. Okay, and so we want to calculate that quantity there. Do we know m1? Yeah, we know m1. It's 7. Okay. Do we know v1x? Yeah, that's 200. Okay. Do we know m2? Yeah, that's 8. V2x, yeah, we just found that. That's 75 right there. Okay. And M3 we know is 5. Put that in brackets like that, just to be consistent. Okay. And do we know V3x? Well, no, we don't, but that's what we want to calculate. Okay. Now I set that whole thing equal to 0. All right. And you say, well, why did you set this whole thing equal to 0, all this equal to 0? And remember that the momentum before is 0, both in x and y. Okay, and so the total momentum after, even though it's got like all these pieces to it, m1 v1x, m2 v2x, m3 v3x, when you add up all those pieces together, they have to add up to 0, otherwise momentum isn't conserved. Okay, so students often get confused and they go, well, how do you know it's equal to 0? And again, at that moment, this equality right here, okay, that's the equality where, students will say, well, what do I do next? How do I calculate this? Because you're thinking, I need to plug in everything to calculate it, put it into my calculator, but we're not working with that. We're working with like just making sure that both sides are equal, and we have to find v3x such that both sides are equal. And so we know that the momentum after is this entire expression, and we know that the momentum before is that expression, so those two have to equal one another. Okay, and it's really easy to solve, so I didn't bother showing you the math. You just do 700 times 7 times 200 plus 8 times 75, okay, and bring that to the other side so it becomes negative, and then divide by 5, and you get that v3x is equal to 100. Okay, let me put that actually on the next line so that it's a little easier to see here, like that. Okay, there we go. So basically this is the expression for the momentum after the explosion before we plug in the numbers. Here it is after we plug in the numbers, and we have to set that equal to 0 because momentum is conserved. Okay, because momentum is conserved there, like that. All right, and then just solving for v3x, that's equal to negative 400. Okay, now let me see if there's any questions so far. Oh, looking good. All right. Okay, and then for the y, it's the same thing again. But it's the same expression, but now you just replace the x with y. All right, so that you have that the expression for the y component of the momentum after the explosion is going to be m1 v1 y component plus m2 v2 y component plus m3 v3 y component, like that. Okay, and then substituting in the numbers, m1 is 7, m2 is 8, and m3 is 5, like that. Okay, put brackets around that just to be consistent. Okay, like that. Okay, now what about v1y? Well, if you remember, m1 was purely along the x-axis, and so there was no y component, and so that's why v1y here is 0. Okay, v2y, so v2 was along the 60 degrees to the x-axis, and so it was sine of 60 degrees. So multiplied by the magnitude, 150 sine 60 degrees, that was 129. So over here we have 129, and then plus 5 times vx has to equal 0. Okay, and you go, well, why is that equal to 0? Same thing as before. Okay, so the total momentum is conserved, and you know that the momentum before is 0, so therefore this entire expression after must also be 0. Has to be 0 before and after. Okay, and so working that out, you will get that number right there, like that. Okay, so now we have the x component of the velocity for m3, negative 400, and the y component, negative 207.84, like that. Okay, and you'll notice that both the x and the y are in the negative direction, and that's what we intuitively expected, because if you take a look at this diagram, you expect that if both m1 and m2, let me use some different colors here, m1 here, no, that's still green, I don't know, let me use purple here, m2 here and m1 here, they're sort of both going in the right direction, towards the right, towards the positive x direction. Okay, and so it makes sense that that has to be balanced with an x component over here in the negative x direction. So the negative x from m3 is balancing the positive x from m1 and m2. Okay. Similarly, m1 and m2, they're both kind of upwards. Well, m1 doesn't even have any component. I shouldn't say upwards in the positive y direction, but m2 has a positive y component to its velocity, and therefore it has a positive y component to its momentum, and that has to be balanced with a negative y here from m3. Okay, and that's why both the x and the y component of the velocity of m3 have to be negative. All right, so that answers these two questions here. Okay, what is the x component and what is the y component of that third piece? Okay, now the next one is what is the magnitude of the velocity? So again, this is going back to when we studied vectors. You know, what we just solved for was x and y component, was Cartesian. All of our problems have to be solved in Cartesians. Okay, all of our formulas are in Cartesian, and the reason for that is because the Cartesian formulas and in the x direction and the Cartesian formulas in the y direction, they totally decouple. Like there's no mixing of x and y. Okay, and so because there's no mixing of x and y, that makes it easier. Whereas if you did this in polar, the formulas would be horrible. And so that's why, you know, we work in Cartesian, but sometimes we want the answer in polar. In fact, I gave you the original in polar because, you know, when I say something like, you know, something is flying off at a certain angle, well, you know, there you go. Okay, that's polar. Okay, so now I'm going to ask for the magnitude and the angle. Okay, so the magnitude and the angle. All right, and you remember, how do you get that? The magnitude, so v3 is made up of v3x and v3y, like that. And the magnitude is the square root of the x component squared plus the y component squared, like that. And then you take the square root of the whole thing. So it's basically Pythagorean theorem. Okay, and if you substitute in the numbers we had above, the square root of 400 squared plus 207.84 squared, like that. Take the square root of that, you get 450.77, and I should put the units in there. That'll be in meters per second, like that. Okay, so there's the magnitude. All right, now the other one was the angle. So how do we calculate the angle? So the angle is theta, and it's calculated as the inverse tangent of the y component divided by the x component. All right, but we're in quadrant 3, and in quadrant 3 you have to add 180 degrees. Okay, so if you work this out, all right, you work out the inverse tangent of 207, which is the y component here. So the y component is 207. Okay, and the x component is 400, like that. You work that out and add 180, you get 207.5 degrees. Okay, now that's the angle that's made with the plus x axis. Okay, let's take a look at that diagram. All right, and that means that this angle right here, and I guess I can do it in blue, starting from the x-axis right there. Okay, starting there and going around, round, round. We're at 90 degrees. We're at 180 degrees, and then finally we get to 207.5 degrees there, like that. Okay, so there you go, and it's in quadrant 3. If you hadn't added that 180 degrees, you would have gotten, let me just quickly calculate this, minus 180, you would have gotten 27.5 degrees. So this wedge in here, let me do it in, I guess we can, I've been using green here, purple, right there. That wedge in there that I'm drawing in purple, that wedge is 27.5 degrees. Okay, so if we hadn't added in the 180, you would have gotten 27.5 degrees as that wedge in there. Okay, and that would have been wrong. You know, we've worked a lot with vectors, so you should be able to understand that you could say, although it's probably not as good because it might get a little bit confusing, you could say that this makes 207 degrees with respect to the plus x-axis, or 27.5 degrees with respect to the negative x-axis. Okay, so I mean, I don't know if I want to write that in there, but just to be very clear, if we said, you could either say 207.5, let's put in the 0.5 there, like that, point with respect to, that's a WRT, sorry about that, with respect to the positive x-axis. Okay, like that. Okay, which is the way we've been doing it up till now. But I think you understand that another way to think about this is that it's 27 degrees, 27.5 degrees counterclockwise with respect to the negative x-axis, like that. Okay, so you can measure angles with respect to positive or negative x-axis or whatever. However, you must work with the angle with respect to the positive x-axis, and this has been my point all through the course, in order for the cosine and sine formulas to work. Okay, which is why we stick with that. In other words, in order for these formulas to work right here, in order for that formula to work, to get the x component, and for this formula to work to get the y component, that angle must be measured with respect to the positive x-axis, like that. Okay, I'm just in passing saying that you could measure the angles with respect to any of the axes, and we've done a little bit of that, but these formulas here, you must measure counterclockwise from the positive x-axis. All right, we've done almost all the problems. Let's do the last one here. How much energy is released by the explosion? Okay, and remember that there are three types of collisions. Okay, so I know you don't think of an explosion as a collision, but it's kind of like an anti-collision, or a collision running backwards in time. If you see two masses, okay, they're like two masses, and they come together and they collide and stick. Imagine running that movie backwards in time. Okay, so the forward movie is two masses come together and stick like that. Okay, run the movie backwards in time. Two masses are stuck together and then they fly apart. Well, think about that. The movie backwards is an explosion. Okay, and that's why conservation of momentum can not only be used for collisions, but it can also be used for explosions. Okay, now when you do that, when you have an explosion, though, the energy after is greater than the energy before. All right, and so that's what's known as a super elastic collision. It sounds kind of weird to say super elastic. Elastic sounds like you're talking about a collision, but for the reasons I just said, a collision running backwards in time is an explosion. Okay, so things whenever you have a situation where there's more energy after the incident than before, you're super elastic. Okay, if you've got less energy after the collision, okay, so two things come together and then they collide and stick, they have less energy after that collision, that's called an inelastic collision. And if there's exactly the same amount of energy before and after, then it's exactly an elastic collision. Okay, so once again, inelastic collision, there's less energy after. Okay, elastic collision, same amount of energy before and after. Super elastic, more energy after than before. Okay, so in this case, it's got to be super elastic, because what's the energy before? Well, back to the diagram, I mean, your mass is just sitting there. That 20 kilogram mass is just sitting there at the origin, and it's not moving. It's not going anywhere. Now, we don't know anything about heat till next semester. We also don't know anything about chemical energy. So you can't say, well, there's energy in the chemical bonds. I know there is, but we don't see it, okay? And so as far as macroscopic physics, which is what we're studying right now, you don't see that there's energy inside of that mass. All you see is the 20 kilogram mass not moving. And the energy is 1/2 mv squared, and if v is 0, then the kinetic energy before is 0, so there's no energy before. Okay, and so where is that? Down here. Okay, so all the energy is kinetic. Okay, and the energy is 0 before. Well, why? Well, because, as I just said, the 20 kilogram mass is not moving beforehand. Okay, now what about afterwards? Well, afterwards, each piece is going to contribute 1/2 mv squared. Okay, now I didn't finish the formula here kind of on purpose. There's the kinetic energy due to the first piece. Okay, and then the second piece will have the exact same form, except that it's going to be the kinetic energy due to the second piece. And then the third piece is going to have the same form again, okay, except that now it's going to be the kinetic energy due to the third piece, like that. And so you're going to have 1/2 mv squared, but for m1 and v1, and then again for m2 and v2, and then again for m3 and v3, like that. Okay, so you just add up the kinetic energy of all three pieces that are moving afterwards, and you'll get the answer. Okay, now those velocities are actually magnitudes. When it comes to energy, it's not a vector, so there's like no x and y component. Okay, so none of that business. It's just the magnitude. Okay, and so you've got v1 here. That's the magnitude of the first one, and we know that that's 200. We've got V2 here, and that's the magnitude of the second one. I know we broke it up into X and Y, but like I said, you don't have to worry about that here. That's the 150. And then V3, that's the magnitude, which we just calculated. We just found that the magnitude was 450.77, like that. Okay, and so that's what you're going to put in for V3 there. Okay, so substituting in, we're going to have 1/2 7, which is M1, 200 squared. Okay, plus 1/2 M2, which is 8, V2 squared, which is 150 squared. Okay, and then we have 1/2 M3 is 5, V3 was 450.77 squared, like that. And you work that all out and you get this number here, which just rounds off to 738 kilojoules. Okay, so that's how much energy is released in this explosion. Okay, maybe we should just write that. This energy is released in this explosion. Okay, now we know that really energy is not created. It's there somewhere before. That's all in the chemical bonds. Okay, so you've got like all these tiny little chemical bonds in there, and they're all like little tiny springs, little compressed springs with energy in them. Okay, and when the explosion goes off, it's like they all spring and they all give their potential energy up to the pieces of the bomb, and that's what causes the bomb to fly apart. Okay, so there you go. Energy before is 0. Energy after is 738 kilojoules. Maybe I should just say here, put a little comma in there. It's 737,983.898 joules, and that just rounds off to 738 kilojoules. Okay, and maybe we should also just say this explosion is super elastic. Okay, like that. All right, let me see if there's any questions, and otherwise we'll just move on. Okay, it doesn't look like there's any questions. We've got 7 people in the chat. That's not too bad. All right. Spend another sec. Okay, we're good. Let's go on. Okay, so that was our 2-dimensional momentum problem. Okay, we did quite a few in class, and there's quite a few in the other tutorial videos, and also in the lecture itself. So I don't want to do too many repeated problems. Okay, I recall that we did not do one of the bomb explosions together, so I thought we'd do one of those. Okay, now this one we've kind of done one like this before, but it's probably worth going through it because there's a lot of steps to it. All right, so I've got 3 masses that are in a straight line along the x-axis. Okay, and M1 is 2 kilograms, and it's at x is equal to 0 meters. Okay, that's along the x-axis. We'll draw a picture. Okay, M2 is 3 kilograms, and it's at 1.5 meters along the x-axis. And M3 is 4 kilograms, and it's at 2 meters along the x-axis. Okay, so let's draw that picture first so that we can see what's going on. Okay, now you should be able to do a 2-dimensional center of mass problem, but and moment of inertia problem. But let's just do a 1D because we did do it 2D together in class. Okay, so what we have here is just all these masses are along the x-axis here like this. Okay, and here's the origin right over there. That's going to be my x equals 0. All right, so this is plus x like that. All right. Okay, and if you reread the problem, M1 is 2 kilograms, and it's at x equals 0. Okay, so I guess we can make these masses red. So right here, this one is M1, like that, and it is at x1 is equal to 0, like that. Okay, now M2 is at 1.5. All right, so we move along here to say here. Okay, and this is where M2 is, and x2 like that is going to equal, what did I say, 1.5. Okay, 1.5 like that meters. All right, and sorry, that was M2. And then we had another one, and it was at 2 meters. Okay, 4 kilogram at 2 meters. Okay, so if that's 1.5, then 2 meters would be somewhere like right there, because it's going to be only half a meter away there. Okay, and so here's M3, and it's going to be at x3 equals 2 meters. Okay, so if I were to draw a distance in here, if I were to draw that distance there, like from there to there, That distance is 1.5 meters. Okay, we'll need that in a minute. But this distance here, okay, that distance there is only half a meter. And you go, why is it only half a meter? Well, if you take a look here, from 1.5 to 2 is only half a meter distance. Okay, so that's what's going on there. All right. Now, let's go back and see what questions I asked. The first question is, where is the center of mass? And the second one, we'll do these two together. Where is the moment of, or sorry, what is the moment of inertia around an axis which is perpendicular to the x-axis and goes through M2? Okay, so for the first one, the center of mass, there's no question of like axis or anything like that. Okay, it's just like, where is that center of mass? Okay, and so the formula for that is given by this. Okay, now there's a numerator and a denominator. This is what's known as a weighted average. And so on the top you have, whoops, these should not be v's, these should be x's. X, and x, like that. Okay, you have m1 v1x plus m2 v2x plus m3 v3x. Okay, that's in the numerator. In the denominator, you just divide by m1 plus m2 plus m3, like that. Okay, and now it's just a matter of plugging in the numbers. So I gave you the number here: 2 at 0, 3 at 1.5, and 4 at 2. So 2 at 0, 3 at 1.5, and 4 at 2 divided by 2 plus 3 plus 4, and that just works out to 1.39, okay, or roughly 1.4. All right, so let's go back to that diagram and just see where that is, 1.4. All right, so whoops, click the wrong thing here. All right, so where is that? Where is this center of mass? I will draw it in red here. So if this is 1.5 where M2 is, this is approximately where the center of mass is, right there. Okay, so there's your center of mass. All right, now I'll erase that in just a second, but you can kind of see that it's roughly in the middle of the object. I mean, you know, M3 is 4 kilograms, and what's M2? Sorry, M1 is 2 kilograms, and so the M3 pulls it a little bit closer its way than M1, because M3 being the bigger the mass, the more it tends to pull the center of mass towards it. Okay, because it's a weighted average, the bigger mass tends to, you know, pull the, like I said, pull the center of mass towards it. So M3 is going to have the center mass closer to it than M1, but you know, it's roughly geometrically in the center of this. Okay, now there's no need for any axis of rotation or anything like that, but for our next problem, let me just erase that center of mass because we don't need it. Okay, for my next problem, in fact, let's erase a little bit more stuff here, because it's getting a little bit yeah, well, actually, let me erase a little bit more. Yeah, and I'll just draw this back here. Like, oh, actually, you know what? Let me redraw the whole diagram, because for the next one, I'm gonna have to just kind of redraw stuff anyhow. Okay, so the next one says, okay, what is the moment of inertia about an axis which is perpendicular to the x-axis and through M2? Okay, so let's go back here like this. So M2. Let me draw them in here again. This one's M1. This one was M2 here, like that. And this one was M3. We're going to put an axis of rotation. Let's make it in blue. We're going to put it perpendicular to the x-axis. That means 90 degrees to the x-axis, like that. And going through M2 like that. Okay? So there we go. All right, so there's our axis, and that's 90 degrees there, like that. So it's perpendicular to the x-axis but goes through M2, and this thing would rotate around there like that. Okay, all right, so I want to know the moment of inertia around that axis. So for the moment of inertia, you don't exactly work with x along the x-axis, you work with r's. Okay, and the r values are, r1 is going to be this distance right here, from the axis to, oh, that wasn't very straight, from the axis to M1. Okay, and we know that we call that one r1, and that one is 1.5 meters. Okay, and you go, how do you know that? Well, we know that M1 is at 0 and M2 is at 1.5, and so that distance in there must be 1.5 meters. Okay, now what's r2? Well, M2 is right on the axis, so R2 is just going to be 0. because the distance from the axis to M2 is 0. It's right on it, okay? And then from the axis to M3, that one is called R3, okay? And we know that that distance is 0.5 meters, like that, okay? All right, 0.5 meters, like that. Okay, why? Because M2 is at 1.5 and M3 is at 2. So between 1.5 and 2 is 0.5, okay? And so, sometimes students will get confused between the moment of inertia and center of mass. The center of mass is using x values measured off of the x-axis, and the moment of inertia is using r values measured from the axis. So irrespective of where you put the origin or anything like that, it's simply the distance from the masses to the axis, and the axis there is in blue, okay? So once again, M1 is 1.5 meters from the axis, M2 is 0 meters from the axis because it's right on it, and M3 is 0.5 meters. Okay, now we can plug into the formula, all right? And the formula just basically is this formula right there, okay? It's not a weighted average or anything like that. You just add mr squared for each of the masses, okay? So we've got 3 masses, so we're going to do m1 r1 squared plus m2 r2 squared plus m3 r3 squared, okay? So m1 is 2, and r1 is, I don't know why I put a negative there. There shouldn't be a negative, okay? So r1 is 1.5, and then we square that, okay? M2 is 3, but R2 is 0, so it's going to be 0 squared. And M4 is 4, okay? And M3 is 4, and R3 was 0.5, so it's going to be 0.5 squared, like that. And, just putting that in your calculator, let me just make sure I did that right. It looks like let me bring up my calculator. I don't know why that doesn't look right, but I think it is, maybe. Let me see. Yeah, it is 5.5. Okay, so that turns out to be 5.5 kilogram meters squared. Okay, so there you go. There's the second question. The second question was, what's the moment of inertia? And there it is. Now, keeping the axis in the same place, what is the torque due to a 4 kilogram force applied to M1 at 30 degrees to the axis? Okay, now this is slightly ambiguous, and I'll show you why when we get to the diagram. Okay, see, the axis right now, I have it in the plane of the paper. Okay, let me clean up that diagram. All right, let me just clean it up here, and let me put the axis coming straight out at you. Okay, now there's no way for me to draw that because I can't draw in 3 dimensions. But that blue dot that you're seeing there, picture that dot is actually being straight out of the page coming at you, so that when I press on M1, okay, so when I press on M1, it's gonna, like, if I press on M1 this way, then this whole thing is going to start to rotate that way. Okay, so that's why I had to change the perspective. It's really the same diagram I had a minute ago, but all I've done is I've just, instead of having the axis in the plane of the screen, I now have the axis coming out at you. Okay, so there it is. And then I say, keeping the axis in the same place, what is the torque due to a 4 kilogram force, okay, applied to M1 at 30 degrees to the x-axis? Okay, so we're going to take M1 here, and we're going to apply a force like this. Whoops, that looks like 60 degrees. Let's do that. Okay, at 30 degrees to the x-axis, like that. Okay, and this force here is going to be, I said, 4 newtons. Now, I said a minute ago this is ambiguous because you said, well, is that 30 degrees to the x-axis, or is this 30 degrees to the x-axis? Okay, like that. And guess what? For the torque, it does not matter. It'll actually work out to be the same both ways. So, even though you're saying, well, what exactly am I supposed to be picturing? Am I supposed to be picturing, let me draw it up here just very quickly. Am I supposed to be picturing, when you say at 30 degrees, am I supposed to be picturing this way with the 30 degrees here? Or am I supposed to be picturing here, I'll do it in a different color, this way with 30 degrees there? Like, which one is it? And my answer is, yeah, there is an ambiguity, but it doesn't matter. both will give you the exact same torque. Okay, and that's just because of the symmetry. And you go, well, why? Because you see, it's not so much the component which is to the left or right. See, this has a mirror symmetry left and right. So it's not the component of the force this way or the component of the force that way. Neither of those matter. It's the component of the force this way. And you see that both the red and the green have the same component of the force, perpendicular to the x-axis there. And so whether you did the 30 degrees one way or the other doesn't matter. Okay? So that's what we're doing. The picture you see here is I'm applying for, oh, that's a terrible end. Let me redraw my end there. There we go, like that. That 4 newtons of force, I'm applying it to M1 right here. I'm pushing, but I'm not pushing perpendicular to the x-axis. I'm pushing at 30 degrees to the x-axis, like that. Okay, and so this is not at all the most efficient use of that force. I could get much more torque out of that force if I pushed perpendicular, but for this problem I said no, I'm going to push at 30 degrees. The only other thing you need to know for a torque is you need to know that distance in there. We had it, I rubbed it off, but let me just put that distance there like that, and that distance R is, we called it R1, is 1.5 meters, like that. Okay, all right, so now what? Well, let's calculate the torque. All right, because I said, what is the torque? That's what we're asking. Okay, so the torque is given by this formula here. All right, tau, I know it looks like a T, but I can't, in my word editor, I can't do tau. Okay, tau, all right, tau is equal to RF sine theta. Okay, where theta is the angle that the r vector makes with the f vector. Well, the r vector was along the x-axis. Let me just look and show you again. Okay, the r vector, which is in green, is along the x-axis. The f vector there is, at 30 degrees to it. So that's the angle that you use in there. Okay, so r we decided was 1.5. The force I said was 4 newtons, and the angle is 30 degrees. And if you work that all out, that turns out to be 3 Newton meters. Okay, so torques are measured in Newton meters, so this torque is 3 Newton meters. Okay, and that answers this question right here. Okay, so keeping the axis still perpendicular to the x-axis, the axis of rotation, keeping the axis of rotation perpendicular to the x-axis. Okay, we're going to push with a force of 4 newtons at 30 degrees. You're going to get a torque of 3 Newton meters. Okay. Now the next question is, what is the angular acceleration of the system? Okay. And so the angular acceleration is given by this formula here. Tau is equal to I alpha, which is the angular equivalent of it's the angular equivalent of F is equal to ma. So it might be worth just looking at this. F equals ma, like that. Okay, so the angular equivalent of force is torque. Okay, the angular equivalent of mass, the angular equivalent of mass is moment of inertia, and the angular equivalent of acceleration is angular acceleration. Okay, so tau is equal to I alpha really is F equals ma. All right, so it's just in its angular form. And I didn't do this for either the calc or non-calc students, but you can actually start with F equals ma and convert everything to their angular equivalent, and F equals ma would just turn into tau equals I alpha. Okay, so they really are the same formula. They just don't look like it because I'm not showing you how you go from the linear quantities to the angular quantities, but if you convert your linear quantities into angular quantities, you'll get tau is equal to I alpha. Okay, enough of an aside. So we wanted alpha, so that's just going to be tau divided by I, and tau we said was 3 Newton meters. Here, where did we calculate that? Right there. Okay, and I was right here, 5, and so you're going to get that. Okay, now this is a little easier than what I did in class. Okay, and that's because in class I actually had 2 forces, and when you have 2 forces, you can get 2 torques, and then you have to worry about adding them together, and you have to worry about whether the torques are clockwise or counterclockwise. Okay, so this is the answer because we only had 1 force here, but let me just show you how that would work. Okay, so over here, if we take a look at this diagram, okay, we have this 1 force here. Let me draw another force in green. Suppose I applied another force here on the 3 kilogram mass like that. Okay, Oh, that's a terrible. Like that, okay? And I don't know, it doesn't matter how big it is, but this could be like another force there like that. And the axis of rotation, it's still around this blue dot right here, okay? So the blue dot is the sort of fixed point. Everything rotates around that point, okay? So in other words, you know, M1 could rotate this way, or it could rotate the other way like that, okay? But the point in the middle is fixed. Or M3 could rotate this way, or it could rotate that way, okay? But of course they're fixed by a bar. Now let's think here. This F here, that force right there, okay? If it's pushing on M3, what would it want M3 to do? It would want to make M3 rotate this way, and simultaneously it would want to make M1 rotate that way, okay? You got to picture the entire bar there is kind of fixed, okay? Fixed like that. That entire bar is fixed, and it rotates around the big blue dot there like that, okay? And so then, this force here wants to make things rotate. What is that? That is counterclockwise. So this force here leads to a counterclockwise torque, okay? What about the red one? Well, let's do this. I don't know what color I can pick here. Purple. Okay, let me pick purple here. This force here, now I know it's at an angle. That force right there is at an angle, but it's got a little bit of a, positive y direction there like that. So it would want to, actually let me pick a different purple, a lighter purple. This one has like a component up that way. So it would want to make M1 rotate this way, and conversely it would want to make M3 rotate that way. And you look at this and you go, oh, so this F here wants to make this thing rotate clockwise. And so this force would give rise to a clockwise torque. Okay, and so if you have a counterclockwise torque, this would be a positive torque, and the clockwise torque, that would be a negative torque, and they're actually competing against one another. Okay, so when you go to add them, you would take the clockwise torque and make it negative, or the clockwise torque would be negative. The counterclockwise torque would be positive, and when you ever add those two together, that would give you the net torque. Okay. Now I did do that one like that in class, so I didn't want to repeat that, but if I had another force in there, that's what you'd have to worry about. By the way, you could have all the forces acting the same. You know what? It might be worth just looking at that very quickly. Okay. Let me just create another quick diagram here. Okay. Suppose that we have like something like this, and here's the axis coming straight out at you, okay? And I don't know, I'm going to apply a force here like this, and I'm going to apply a force here like that, okay? And you say, okay, well, it has to rotate around that I'm doing it in blue now, has to rotate around that blue dot, has to rotate. So this is a rigid bar that's going to rotate around that blue dot. Well, F1 here is going to make it rotate that way. Okay, and so that is clockwise. But F2 here, guess what? F2 also wants to make it rotate clockwise. So these two forces actually have torques in the same direction. Even though the forces are in opposite direction, the torques due to them are both in the clockwise direction. That's because they're on opposite sides of the axis of rotation, okay? Now, we're going to do more of that next semester when we do statics, but, I just want to make sure that we understand this, that you're not looking at the direction of the force so much as the direction in which the force makes the thing turn. And so you ask, does this force make the force gives rise to a torque. Does that torque want to turn it in the clockwise direction or in the counterclockwise direction? Okay, so there we go. All right, well, let's move on. Okay, and before I do, actually, maybe I should just take a look if there's any questions in the chat. Is everyone doing okay? All right. Just wait a second here, and all right. Let me go on. I'll check back every once in a while. Okay. So now if the system starts from rest, how long until it's spinning at 20 RPM? Okay, so how long before it starts spinning at 20 RPM? So this is a kinematic problem, rotational kinematic problem, because we have the angular acceleration, so we have alpha. That's one of the things we know. And I'm asking for how long. I'm asking for time, t. Okay, it starts at rest, which means that its initial angular velocity is 0. Okay, that's what starts at rest means. and it spins up to 20 RPM, okay, revolutions per minute. So that's its final angular velocity. So there's an initial angular velocity of 0. There's a final angular velocity of 20 revolutions per minute. We have the angular acceleration, and we want to find the time. Okay, so it's pretty obvious that this is a angular kinematics problem. Okay, so let's see what we have here. This is part E. We start off that it starts at rest, so omega naught is equal to 0. Okay, 0 radians per second. Put in the units there like that, radians per second. Okay, and it spins up to 20 RPM. Okay, now remember, revolutions per minute, that's the typical unit that you'll see in the real world, but we have to work in radians per second. Okay, so we got to convert, and we've seen this conversion a few times already. So we have 20 revolutions per minute. A revolution here is 2 pi radians, so that's in the numerator, so put 1 revolution in the denominator is equal to 2 pi radians in the numerator, like that. Okay, and so that'll convert the revolutions there. And then we have a minute, and we got to convert that to seconds. Okay, so 1 minute is 60 seconds. Minute here in the denominator, so put minutes in the numerator. And then turns out that 20 revolutions per minute is about 2.0944 radians per second. Okay, so there's our omega. Alpha we have from the previous problem. It was 0.54545 radians per second squared. Okay, and I didn't write down all of our kinematic equations. You have them in your notes, but if you look through them, you go, well, which one do I want to use? And it's pretty obvious that we need to use the omega is equal to alpha t omega naught, because we want to solve for t. Okay, and it's the easiest of the three, but we've done problems with the other ones. So do we know omega, the final angular velocity? Yeah, it's that quantity right there. We just found that. Okay, so there's our omega, there's our final angular velocity. Our initial angular velocity was rest. Okay, alpha is the angular acceleration, is this 0.54545, and we want to solve for t. And skipping the trivial algebra there, it turns out that t is 3.84 seconds. Okay, so that's how long it takes for this thing to spin up. All right, so what thing are we looking at? Well, let me switch back to that diagram just to show you here. So it's a little bit messy now, but let me see if I can clean out some of the stuff here. And there we go. Okay, so all we have is that 4 Newton force there. And what happens is, let me do it in purple here. This thing starts to rotate. So it starts to rotate and rotate and rotate and rotate like that. Okay, and it starts off rotating with an angular velocity of 0. So that's its initial angular velocity. And I want to know, when is it finally spinning at 20 RPM? Like that. And it turns out that it only takes 3.84 seconds. Okay, so in 3.84 seconds, let me clean that up. Okay, in 3.84 seconds, it spins up to 20 RPM from rest. All right. Okay, a couple more questions for this one, and then we can move on to the last one. At that point, I should say at that point in time, or after it's spun up to 20 RPM, okay, what is the tangential velocity? All right, now we have the angular velocity, and there's a relationship between the angular velocity and the tangential velocity, and that's this formula right here. Okay, the tangential velocity vt. I can't do a subscript, but this is v subscript t right there. Okay, so vt is equal to r times omega. Well, r, what is that? Well, let's go back to the diagram. Okay, right here, and whoops, I think I used the wrong r. Let me reread the problem. I did. We were applying it to M1, and M1 is 1.5, and I made a mistake. That should be 1.5, okay? So let me switch back to there, okay? Well, let me, sorry. That's 1.5 in there, okay? And I had here a minute ago, I just switched it on, you didn't see me, but I had 0.5, that's actually 1.5, okay? So R is the distance from the axis to M1. Oh, I'm sorry, no, I was right. I apologize. Let me go back again. It's a little bit more subtle. I'm not reading my own question carefully. At this point, what is the tangential velocity of M3? Okay, So what is the tangential velocity of m3? We know the angular velocity for the entire system. Okay, that's the angular velocity for the entire system. And it's the same angular velocity for m1, for m3, for all of it, no matter where you are. But now I want the tangential velocity for m3. And I did have it right at 0.5, but let me show you why now. Okay, let me go back here. When you calculate this tangential velocity, we want the tangential velocity, let me do it in purple, for m3 here. We want to know how fast is this tangential velocity here, like that. Okay, well, to calculate that, we know that the angular velocity is going to be that 2.094, and I forget what the other decimals are, radians per second. Okay, we know that that is the angular velocity. The tangential velocity is given by the formula Vt is equal to r times omega. But now you say, well, which omega? Which r? We know the omega, but which r? Well, if we were talking about m1 here, then it would be 1.5. But we're talking about m3, so we want the tangential velocity for m3. And so we say to ourselves, what is the distance? What is r for m3 between the origin and the axis of rotation? And that distance there, let's do it in green, that distance there is 0.5 meters. Okay, so I got to tell you what object we're talking about, because you need the r for the object that we're talking about, or the point, or whatever I'm referring to. Whatever object I'm referring to that I say what's its tangential velocity, I got to give you enough information so that you can figure out what r is. And r is the distance from that object to, it would be right here, to the axis of rotation. And in this case, it's 1.5. Even though the force was being applied at 1.5, the m3 is at 0.5, and that's the one that we want there. Okay, so I hope that was clear, but that's why we have 0.5 in there. Okay, and then working that out, we get that the tangential velocity for m3 when it's spinning at 20 rpm is 1.0472 meters per second. Okay, let me see if there's any questions with that. All right. So yeah, I confused myself there because I thought I was calculating Vt for m1, and m1 is 1.5, but m3 is only 0.5. And so since we want the tangential velocity of m3, we actually want only 0.5 there. Okay, and I think I asked the same thing for the centripetal acceleration. Yeah, so what's the centripetal acceleration for m3? And the centripetal acceleration for m3 is given by this formula here. Okay, AC, the centripetal acceleration, is r omega squared. Okay, and again, omega, that angular velocity, is the same for all of them. It's just how fast is it spinning, and there's no one mass that's spinning any faster than the other as far as omega goes. Okay, but its tangential velocity, of course, depends on how far you are from the center, and its centripetal acceleration also depends on how far you are from the center. Okay, and so here we have r is for m3 is 0.5, and omega, well, you know, that's the same omega as above, is 2.0944 squared, and so that gives us a centripetal acceleration of 2.1933 meters per second. Okay, and so let me just show you where that is on the diagram here. So what you're seeing there in purple is the tangential velocity, but let me do it in red here. The centripetal acceleration is towards the center, like that, AC. Okay, and the centripetal acceleration is calculated using r omega squared. So they're very similar. If you take a look here, you can see r omega squared looks an awful lot like r omega. Okay, but of course, you know, the acceleration has r omega squared, whereas the tangential velocity has r omega. Again, the r, okay, this is kind of the point of this question, that r is always the r of whatever object you're talking about. In this case, m3, and m3 is 0.5 meters from the axis of rotation. Okay, and that solves that problem. Now, there were some other things I could have calculated, like the tangential acceleration, and I could have also asked for the tangential velocity of m1. Okay, it's the same thing, but you would have used r for m1. Okay, but there it is. That question pretty much goes over everything that we did with uh, um, rotational kinematics and rotational dynamics, including calculation of the moment of inertia. All right, let me take a look in the chat here. All right, looks like everyone's okay. All right, good. So, like I said, I'm not going to do a question on rotational kinetic energy. Okay, that's where you have like 1/2 mv squared for the linear part and 1/2 I omega squared for the rotational part. Okay, so your total kinetic energy breaks down into two pieces. Okay, and this is the only extra piece you have to calculate. Like I've given you lots of these now, and they're all roughly the same. So I just would rather go on to an angular rotational conservation of angular momentum problem. Okay, I think those are a little bit more difficult. So if you still want at the end, if anyone asks, I mean, I could always do one of these, but let's spend our time concentrating on the angular momentum problems because they're a little bit more difficult. This one is similar to what I gave you in class, but I found that students tend to get a little bit confused with this because this is actually a combination of angular and linear momentum, and that always causes a bit of confusion because you've got one thing that's carrying linear momentum, but that linear momentum can also be understood as contributing to the angular momentum, and that's because linear and angular momentum are really the same. Okay, just like tau is equal to I alpha is really F equals ma in disguise. Conservation of angular momentum is really conservation of linear momentum in disguise. Okay, so I didn't actually prove that for either the Physics 101 or 111 class. So, you say to me, well, how is that the case? I didn't really prove that. It's not that hard to prove, but it takes, about half an hour to do it right. And so, given the time I have in these courses, I don't usually prove these things. But if I did, you would see that, yeah, like all you're doing is just taking linear momentum and like dividing out an r in certain places, and you get this angular momentum thing, and you go, well, okay, fine. And it just seems that the equations just seem to apply more easily. Okay, but when you have to glue together linear and angular momentum like we do in this problem, it does cause a little bit of confusion. So let's go through it. Okay, that's enough of an introduction into the motivation for this question. So we have a bullet, and it's a mass of 150 grams traveling at 500 meters per second. Okay, and it's fired into a rod which is of length 60 centimeters and has mass 1.5 kilograms that can spin around its center. Okay, and the bullet hits the rod perpendicularly. Okay, that's kind of important. I'll draw this in a minute. Okay, it hits the rod perpendicularly at a distance of 40 centimeters from the center, and it embeds itself. And of course, as you can imagine, the rod, which is not moving initially, will start to spin. Okay, and how fast does it spin afterwards? All right, so let's take a look. Whoops, there we go. Let's take a look at this. And let me start off with a new sheet here. So we have a rod here, like this. All right, here's my rod. And rods, we can have them spinning around one endpoint, but I have the rod spinning through the middle here like that. So that black dot right there, that is my axis of rotation, and it is pointing up at you. Okay, so that this rod could spin like this. Okay, it could spin like that. Or conversely, it could spin even the other way like that. But whichever way it spins about that middle point there like that. Okay, great. Now we have a bullet, and the bullet is, let me draw the bullet right here. Okay, there's this bullet. It's going to come in and it's going to embed itself 40 centimeters from the center. Okay, so the rod is actually, what did I say here? Oh, it can't embed itself 120. I'm just going to change this behind the scenes here. Oh, I can't do that. Hold on. Yeah, I made a tiny mistake. I just realized that it can't, because if it's only 30 centimeters, then it can't embed itself. Well, we'll say 20. All right, I got it. All right, I changed something behind the scenes. I'll show you in a minute, okay? So the entire rod is actually, this entire rod here is 60 centimeters like that. Okay, so the length of the entire rod is 60 centimeters. All right, which means that from the middle to here is 30 centimeters, like that. And the bullet only embeds itself. Well, I wrote 40 centimeters, but I'm going to make it 20 centimeters because obviously it can't be 40. Okay, so the bullet, it's only going to embed itself 20 centimeters from the center like that. Okay, so there we go. The bullet's going to embed itself, and I think you can imagine what's going to happen. As soon as it does, this thing is going to go spinning like that. Okay, and the bullet's going to be embedded in there. Here, I'll draw it in blue there like that. So here's that blue there, that blue squiggle is the embedded bullet, and it just goes spinning around like that. Okay, and I want to know how fast is it spinning. So I want to find that omega primed after the collision. All right. So so what did I change? Well, a minute ago I had 40 here. That has to be 20. Why? The entire rod is of length 60. So half the rod is 30. So, if the bullet is at 40 centimeters from the axis, well, it's going to miss the end of the rod, which is only 30 centimeters beyond the center. Okay. So, yeah, it was just a minor oversight. I thought 40, is less than 60, but the entire rod is 60. Okay. So half of the rod is 30. And so I just changed that. A minute ago I had 20, and now I have a minute ago I had 40, now I have 20. Okay, so let's do this. Well, maybe I should just say, how do you calculate angular momentum? Okay, so angular momentum is just I times omega like that. All right, so we have to calculate I and we have to calculate omega. All right, so let's calculate I for both the bullet and the rod. All right, so the moment of inertia for a rod spinning around the center, that's one of those formulas that I gave you. Okay, so the test is open book, so you can look these formulas up. So when a rod is spinning around its middle, the moment of inertia is 1/12 ml squared, where L is the total length of the rod. Okay, 60 centimeters in this case. When the rod is spinning around one of the end points, then it's only 1/3. So make sure you know the distinction. In our case, let me go back to the diagram here. We were spinning through the middle, okay, where that black dot is. So we want the formula that is 1/12 ml squared. All right. If it were around one of the endpoints, let me just show you that here. So I'll do it in red. I'll take this out. But if it were spinning around that spot right there, okay, it's not in our problem. But if it were, then we would use 1/3 ml squared. Okay. So over here, the rod, the moment of inertia is 1/12 ml squared. So that's 1/12. M, I said, was 1.5 kilograms, M, and the total length is 0.6 squared, and that gives me that number right there. Okay. Now, the bullet, I did this wrong, but I'll just recalculate it. The bullet, mr squared, that is correct. Okay, but now I should be actually using the number 0.2 there, like that. And let me just quickly calculate that on my calculator. And I get 0.06 like that. Okay. Now, you say to me, how did you get this formula for the bullet? And why did you use 0.2 for the R? Okay, so let's go back to the diagram and you'll see what's going on there. Okay. And you know what? Let me clean up the diagram a little bit here. Okay, so this is the before picture. Okay, once the bullet is embedded, let's take a look at where that bullet gets embedded. It gets embedded right there. I had it drawn in there, and there it is right now. So that blue dot is where the bullet is embedded. Now, when the bullet is embedded and it's spinning around the axis of rotation, where is that bullet spinning? It's spinning like this, isn't it? And that's not a circle, but you got the idea. What's the radius of that circle? Well, that radius of that circle, R, is how far did the bullet embed itself from the axis? Well, I just told you a minute ago, it embedded itself 20 centimeters, like this. In other words, 0.2 meters, like that. Okay, there's your R. And you say, but out here, what's the R out here for the bullet? It doesn't matter. We're really not worried about the bullet until it embeds itself. So up until it embeds itself, we're not really worried about what its moment of inertia is. But once it's embedded, it's going to be traveling in a circle of radius R. And so it's a mass M traveling at around an axis of rotation at a radius R. And a mass M at a radius R has a moment of inertia, mr squared. Okay, just like we saw a minute ago with our point masses that made up those those three masses in a row. Okay, and so that's why you use this formula right here. Okay, and that's a little bit subtle because the bullet is moving in a straight line, but as long as it's moving in a straight line, it's really not part of the problem. It's when it gets embedded and it's starting to travel in a circle, that's when it's got a moment of inertia, and that moment of inertia is its mass times its radius squared. And there it is. So the mass was 150 grams, or in other words 0.15 kilograms, at a radius of 0.2 squared, and so that gives me 0.006. Okay, great. Now, we needed those moments of inertia. Okay, we needed those moments of inertia, and there they are. There it is. But now we want to calculate the total momentum before and the total momentum after. So the total momentum before is the moment of inertia of the bullet times the angular momentum of the bullet. So that's the angular momentum of the bullet plus the angular momentum of the rod before the collision. But before the collision, the rod is not turning. And so the angular momentum of the rod is 0 before. Only the bullet is carrying any angular momentum before the collision. Okay. Now you say to me, well, wait a sec, before the collision, it's not even moving in a circle. Yeah, you can think about it as just at the moment when it collides. At the moment it collides, it is right on the circle. It's like entering into that blue circle. And so at that point, you could say, okay, yeah, this bullet kind of has an angular velocity and a moment of inertia. Okay. Well, the moment of inertia we just calculated for the bullet. Okay. The moment of inertia was, this number right there. Okay. What about the angular momentum? Well, the angular momentum is just the linear momentum divided by r. Okay, so it's the linear momentum divided by r. And r is 0.2, and I know I have 0.4 here because, like I said, I made a mistake. So let me fix that. And what's that going to equal? Should be twice the value that's there, 2,500. Yeah, okay, that's what I thought. Okay, good. 2,500. Okay, so v is the velocity, the linear velocity of the bullet, divided by r. Okay, like that, and that's going to be 500 divided by 0.2. And you say, well, wait, where did you get that? That's like your tangential velocity. At the moment the bullet gets embedded, its velocity, its linear velocity, is its tangential velocity. And the tangential velocity can be related to the angular velocity by omega is equal to v over r. Well, above we didn't have that. Above we actually had here, I'll just put it parenthetically, we had vt is equal to omega r omega like that. Okay, that's the way we had it written above. But if I divide both sides by r, then I get v over r, and the linear velocity v is its tangential velocity at the moment that it gets embedded. So that's how you go from the linear velocity, 500 meters per second, to its angular velocity of 2,500. Whoops, that should be a 0 there. 2,500 radians per second. We'll even put a radian in there like that. Okay. So that's a little subtle, I agree. So you just have to really think about what's going on there. And to get that straight in your head, I always like to think about what's going on right at the moment that it gets embedded. Right at the moment that it gets embedded, its linear velocity is its tangential velocity. Okay, so the tangential velocity is 500 meters per second at the moment it gets embedded. And to go from a tangential velocity to the corresponding angular velocity, you just divide by r, which is 0.2. And that's what we did right here. Okay, that's what we did right here. There's the linear velocity, divide by the radius, and that gives me 2,500 radians per second. Okay, so that tells me, if I plug back into here, that my this is totally wrong. Whoops. That's okay. We're doing it together. So the it's the moment of inertia of the bullet, which is this number right here. Okay, multiplied by the angular velocity of the bullet, which is right there. Okay, and that's going to equal, I'll tell you in just 1 second, 15. Okay, 15. You say, well, what are the units? Well, the units of the moment of inertia are kilogram meters squared. So, whoops, right here. Kilogram meters squared. That's just for this part, okay? And the units for the angular velocity are radians per second squared. That's this part here. But you can drop out the radians because they're dimensionless anyhow. And so there are the units right there for angular momentum, but they're kind of weird units. Okay, so like there's no special name for them. Okay, but there you go. There's the MKS units. Okay, so there's the total momentum before. Now the total momentum after the collision is not going to equal 30. It's going to equal 15, like that, because L is conserved. Okay, so it's 15 because that's what we got before the collision. So the total angular momentum before the collision was 15 kilogram meters squared per second. So the total angular momentum after the collision has to be 15 kilogram meters per second squared. So that's where this is coming from. Okay, but what's this? Well, first of all, both the rod and the bullet are rotating together. So if I ask what's the angular velocity of the rod or what's the angular velocity of the bullet, it's the exact same angular velocity because they're rotating together. And that's why I have just an omega prime there. Okay? So they're rotating together. Well, if the angular velocity is the same, then the moments of inertia just add. So I have the moment of inertia of the bullet, okay, which is not that number, but this number right in here. Okay? So there's the moment of inertia of the bullet. 0.006. Okay, there it is there. 0.006, 0.006. Okay, and then the moment of inertia of the rod, we calculated up here, was 0.045. Okay, so down here we have 0.045 multiplied by the unknown angular velocity after the collision, and that's got to equal the 15. Okay, the 15 right there. All right. Now, this is obviously wrong, and that's obviously wrong, okay, because I'm using the wrong numbers. But let me add those numbers together first. Okay, we'll do it one step at a time so we don't make a mistake. And I get this. I get that this multiplied by omega primed is equal to 15, like that. Okay, so what did I do? I just added those two together and I get that. And then I get that omega primed is equal to, what do I have? Okay, 15 divided by 0.015, and I get this number right here. All right, like that, radians per second. Okay, that is the answer. Okay, but radians per second are not that intuitive. And so as the last step, even though that does answer the question, let's convert it to revolutions per minute. And so we're just going to take that number there like that. Okay, and that's in radians per second. So we got to convert, okay, the radians to revolutions. So radians in the numerator, radians in the denominator. 1 revolution is 2 pi radians, like that. Okay, so there's, that's equal to 1. And then the second here, we want to convert to minutes. Whoops, another mistake there, like that. Okay, and so seconds in the denominator here, so seconds in the numerator, 60 seconds is equal to 1 minute, like that. Okay, and here, let me just revolutions per minute, like that. Notice that the radian here will cancel radians there, and the seconds there will cancel seconds there, and all that remains is revolutions per minute. Okay, revolutions per minute. And then of course I got to do the math. I got to take that number there, multiply it by 60, divide by 2 times pi, and that gives me this number right here. Okay, there you go. There's the answer in revolutions per minute. Now, we don't usually write revolutions per minute that way. That's the better way for us to write it, because then you know that it's revolutions in the numerator and minutes in the denominator. But more likely you will write this as RPM, like that, or you'll see it written as RPM, like that. If you take a look on your car, like it's called the tachometer on your car. That's like the thing that says how fast your engine is spinning. and it's like usually most car engines will idle at about 700 RPM. So you'll see a gauge on the side of your car. Like my car's a standard transmission, so the RPMs are important. Okay, so you'll see there, you know, it usually idles around 700 RPM. The gradations are usually in thousands of RPMs, and you will see the number as actually RPM like that, but it means exactly revolutions per minute. Okay, so let's conclude. You know, take a look at the picture again. Before, you know, the stuff that's in black there, there's your before. Okay, and the rod is just sitting there, and the bullet's coming in at 500 meters per second, so it's really moving along there, and it gets embedded at that blue spot. Okay, which is 20 centimeters from the black spot, which is the axis. And of course, as soon as it does, the bullet and the rod they're both going to be spinning really fast. Okay, so the rod wasn't spinning, but then of course after it's hit by the bullet, it's spinning. And I asked the question, how fast is it spinning after the collision, after the bullet, you know, hits it and gets embedded? And the answer is it's spinning about 2,800 RPM. Okay, and there you go. That answers that question. Okay, so let me just highlight a few of the things that students tend to find difficult with this problem. Okay, because I've given these problems in the past, and you know, the problem I skipped here, the one with like the energy problem, students tend to do just fine with those. But for some reason, like this one seems to be just the math isn't hard, but it tends to be a little conceptually demanding, and so I like to do it a couple of times just to really get clear what's going on. And it always has to do with the bullet. Okay, the thing that's going from linear to angular. Okay, so the first is even though the bullet is moving along a straight line, you can think of it as having an angular a moment of inertia. And you go, well, why? Well, because it's got a mass, and when it starts to spin, because it's going to get embedded and start to spin, it has a radius, and a mass m spinning at a radius r has a moment of inertia mr squared. Well, you know m, 150 grams or 0.15. You know r, it's going to be spinning at a radius of 0.2 meters, 20 centimeters, and so you've got the moment of inertia of the bullet. Okay. Then the other one that's a little bit difficult is the angular velocity of the bullet, because you say the bullet's moving in a straight line. And you go, well, how can a bullet, something that's moving in a straight line, have an angular velocity? That's like how fast it's spinning. How could something that's moving straight be spinning? Well, at the moment when it transitions from going straight along a straight line to going along a circle, you can equate the velocity to the tangential velocity right at this blue point right there. Okay, right there at that blue point. I'll circle it with a red circle right there. Okay, at this point here, it has a velocity v, which is 500 meters per second. Okay, when it hits that blue spot right there, that linear velocity is the tangential velocity. It's the velocity along the tangent of the circle. And you say, well, how fast is that? Well, the answer is 500 meters per second. Okay. All right, so there you go. So then you say, well, is there a way of relating the tangential velocity to the angular velocity? Yeah, Vt is equal to r omega. So omega is equal to Vt over r. But Vt is just v, and so you're back to just calculating the v over r. Okay? And so that's how you go from that linear velocity to the angular velocity of the bullet. Great. If you've got the moment of inertia of the bullet, and you've got the angular velocity of the bullet, and you multiply I times omega, you get L. Okay, you get the angular velocity. All right, and so there you go. The angular momentum is, in this case, 15 kilogram meters per second squared. All right, and then, you know, after the collision, you know, they have a common angular velocity, so their moments of inertia just add, and then the rest of it is straightforward. But it's that bullet part that's a little bit difficult. So there it is. Let me take a look if there's any questions in the chat, and if not, we're done. So let me just ask, is everyone good with what I've done so far? Do you have any other questions? If not, we'll just call it quits. All right, I'm not seeing any questions in the chat right now, so um, there it is. And I'm available all week. And if you want to get on Jitsi in the evening, but even if you want to just ask questions at any time, email me. And we can either set up a time to get together in Jitsi, or else I can try to answer your questions through email. You can say that you have a question through by texting me, so feel free to text me, but don't actually text me a question. It's really hard to answer physics questions using text. Okay, I don't like to text, period, but I'm certainly happy to answer your text to say, yeah, I'll look at, email me the question and say in the text, I emailed your question, could you answer? And I'll answer an email. It's a lot easier for me. Okay, good luck. Bye bye.